everybody. It's the top of the hour, so I'm going to assume everyone's logged in and we're ready to go here. I'm Ronald McCollam. I'm a solution architect at Resin.io, and I'm going to talk to you today about DevOps for IoT devices, so IoT at internet speed. So it's a little odd to be doing this sort of conversation or this presentation in my own living room, just to my webcam. So I'm used to having a big audience of people that I can see. So I'm hoping everybody's out there, and I'm looking forward to getting some great questions. As I'm going through this, if you have questions, please, hi Lucy, I've got a couple of people coming in. If you have questions, please do put them into the chat box. I won't be able to see them as I'm presenting, but I will definitely make sure I leave some time at the end to go back and check on those and answer any questions that you have. So a little bit about me. I am, like I said, I'm a solution architect at Resin.io, which is, I really kind of think of it as a plumbing company for the Internet of Things. So we help people get IoT devices managed and updated remotely. Myself, I am a computer scientist by trade. I'm a Linux geek from way back from when Linux was still in the 1.x days of the kernel. And so I kind of come up at this from a software perspective. I really didn't learn a whole lot about hardware until the past few years when we really started to see a switch from microcontroller-based devices to microprocessor devices. So as we sort of went from those sort of 8-bit microcontrollers into things like the Raspberry Pi or the chip or the Onion Omega or BeagleBone, all of the explosion of Linux devices that are now programmable and usable by people like me who don't always know which end of a soldering iron to pick up. It's been a really exciting time, and I've learned a lot and experienced quite a bit of where the industry is going, both from a software perspective and from a hardware and embedded perspective. And it's really that I want to talk about. So I think this is probably a good time as any for me to share my screen. Oh, that's the wrong button. Let's try this one. There we go. So what I really want to talk about is exactly that, is applying the lessons that we've learned and the tools that we've developed in the software industry, especially the web and software as a service industry in the past 20, 25 years, and bringing that to the embedded world. And that's really what we mean by IoT development at internet speed. And so I really want to set the scene. We'll get into the tech toward the middle or into my talk, but I want to really set out the problem and make sure everybody's on the same page as to where we are in the industry today. Here we go. And this is really what every IoT project looks like. And I think even if you've never built an IoT project, even if you're just a consumer of Internet of Things technologies, you'll really be familiar with this pattern. It's kind of a very simple process to build out an IoT project. And it really starts with devices. So I either build something or I go out and I buy something off of the shelf, and I figure out what that hardware is going to be, and I put some software on that hardware. And so now I've really got my device. I've got a physical object that I can start using and doing something in the world. And so I push those devices out into the world, whether that's in one location, maybe I've got a smart building where I've got a bunch of devices that I'm using to control that building, or maybe I'm pushing these things out by the thousands or tens of thousands, so into the world as sensors, or even into people's homes as, say, set-top boxes or smart thermostats. But I've got all of these devices, and I've got code running on them. So now those things are out in the world, and then the next step is that I want to connect those to the internet. And this makes sense, right? You don't have an Internet of Things without some sort of internet connectivity. So I find a way to connect those devices up to probably a cloud platform, if not something that I'm hosting myself, and I'm going to gather data from those devices. So if I've got sensors out in the world, I'm pulling back sensor data. If I've got things like set-top boxes or smart thermostats, I'm still gathering data from those. I'm learning a lot about what people are doing with those devices and what those devices are doing out in the field, and I'm using that to analyze and improve my devices. And really, if you think about it, at this point, you're basically done, right? You've got devices out in the field doing something, you've got analytics crunching away on those, you've got connectivity. You don't really think you need anything else. Although anybody who has ever used an IoT or bought an IoT project will tell you there's at least one more step. And that is everything just blows up and goes horribly wrong. We know even last week there was an example of a botnet of IoT devices, of things like internet-enabled security cameras attacking major platforms that the internet runs on, taking down DNS, and as a result, taking down a number of sites. So this is a massive problem. This happens over and over. There's something always goes wrong as soon as you put a device out in the field. Now, if you're really, really lucky, there's another step after this blowing up, which is that you get to fix these devices. And this is really expensive and time-consuming and difficult, because you now have to send people out into the field to touch those devices and actually get physically in contact with them and update them. Or maybe you push an update out and you publish that out on your website and you say, hey, everybody can go download this thing and put it on your device and get them all up to date. But it's a really error-prone and difficult process to do this. Nobody really wants to be in charge of managing a bunch of devices that they don't really know what's going on the inside. And similarly, manufacturers don't want to be in charge of managing a bunch of people to go out into the field and update these things. And incidentally, I say you're lucky if you get to that step, because sometimes you just don't. If anybody remembers the Revolve, it was a smart home hub platform. The idea was this was going to be the sort of thing you can put in your home, and you can use this to connect to and control a lot of other devices, a lot of other IoT devices in a smart home sort of environment. And anybody knows what happened to this thing. It's that, Google bought them with Nest, and they kept it going for a little while and then decided it was too much work to keep it updated. So they pushed out one final update and just turned it into a big, expensive brick. So this is, the sort of worst case scenario of where this IoT disaster platform ends up, is that you have bought some piece of hardware wanting to use that, wanting to integrate it into your life, and instead it gets disabled because it's just too much of a hassle to keep updated and keep fixed. So if we go back to this idea of having connectivity and having devices out in the field, we really need something else to complete the picture. There needs to be some way to easily manage and update these devices, keep them running, and keep them operational, so that as new security vulnerabilities are found, or even as bugs in the product need to be fixed, we can push out updates to those devices and keep them going. Honestly, I don't feel like I can overstate this enough. I think this is absolutely critical to IoT gaining mainstream adoption and being something that does become the next game changer in technology. Without the ability to fix errors in the wild, without the ability to patch security holes, this is just going to continue to be a disaster. We have to address this issue. But you might think, well, I've really already got this connectivity. I've got some internet service that is talking to these devices. I can just do this myself. It's very easy to use existing tools that we might use in a data center, or maybe even just through devices that you've kind of homebrewed to do this. I'll just SCP or rsync some software down to the device, and I'll run a shell script to do an update. And frankly, yeah, that works. That is an approach that you can take, and that is basically the approach that people took from the microcontroller world. We'll do an over-the-air update. We'll push everything out, and we'll just run a script that blows everything on the device away and puts the new code on there. The problem with this becomes that if you do a bad push to one of these devices, there's no real way to get back to it. Remember, these are not in your physical control. If you push something onto a device and you can't, and you take down the connectivity of that device, your update crashes, you're now stuck. You don't have a way to get those devices, and you're back to having a team of people go out in the field, physically touch the things, and nurse them back to health. It's an expensive and error-prone process that nobody wants to deal with. And this becomes even more true when you start to think about mission-critical devices. It's sort of one thing when you have a home hub that's going to control maybe your heating system or your radio or your lights from your phone. But when you start talking about IoT devices being pushed into more mission-critical areas, and they are going everywhere. If you do a bad push and you can't fix that device, you're in a real disaster now. I personally don't want to be on a plane that somebody pushes an update to and can't roll that thing back if it goes wrong. Hopefully they won't actually be doing that to planes in flight anytime soon, or at least not while I'm on the plane. But the idea still holds for things like medical devices, even smart buildings. If you push an update that crashes your elevator controllers and I'm on the 100th floor, I've got a long walk ahead of me to get to the street and out of that building. I don't want that to happen. And incidentally, we at Resin know this space really well because we lived this problem. We actually took that approach of using SSH, SCP, rsync, pushing, just blasting things out onto devices. There was a project in the 2012 Olympics in London to do digital signage that the team that eventually became Resin was part of. And we thought it would be just that easy. Just push an update out, run a script, and overwrite it, which is how we had people with computer science degrees, computer science PhDs, walking around in London in the winter with USB keyboards, USB thumb drives, finding all of these devices and fixing them manually. So we knew there had to be a better way to do this. And this is a quote from O'Reilly that I absolutely love. I think this really sums up where what the status of the IoT world is today and where it needs to go. And that's: the web brought about the end of the annual software release cycle. The industrial internet will bring about a similar change in the physical world. And if you think about this, this really rings true. What was software like before the days of the web? You went to a store, you bought a shrink wrap box off of a shelf, you took it home, popped a stack of floppy disks or maybe a CD into your computer, you installed the thing, and you're pretty much done. That was really the last interaction that you had with the manufacturer, or maybe they'll put out a release in 6 months or a year to fix some bugs. But that was really it. It was a really slow cycle with very, very limited back and forth between the deployed software and the software manufacturer, the software creator. Sounds familiar, right? That's where we are with the IoT world today. We're doing occasional updates that are very slow and painful with very little communication between the people that have the devices and the people that are making the devices and making the code for those devices. But we don't have that today. In the web world, the software as a service world, people are doing updates very, very frequently, once a month, once a week, once a day. Think about Facebook. Facebook actually pushes releases to production twice a day. They are updating production code twice per day. And Facebook rarely, if ever, goes down. This isn't an error-prone process. This is something that they've figured out and gotten down to a science. And I'll talk more about that in a sec, but I think we can bring that to the IoT world and bring those same models and make this something that we can do multiple deployments a week or even a day in the physical world. But I want to talk about why the IoT world is in this position and why that's so important. And the chart may be a little hard to read. It may be a little small if you're watching this on the webcast. But I think everybody's familiar with this hockey stick sort of graph. Everybody saw this when telephones and tablets started to take over the internet. This is exactly that sort of graph. We had a bunch of computers on the internet, and then we added telephones and tablets. We added mobile devices, and we got an order of magnitude more devices added, both in terms of speed and in terms of absolute number to the existing infrastructure of the internet. We're actually seeing the exact same pattern happen in the IoT world, only even faster. By 2018, we're going to have more IoT devices on the internet than PCs, phones, and tablets combined. So we're putting tons and tons of new devices out there. And at the same time, these devices are getting more complex. And I mean complex here in really two senses. One of which is the devices themselves are actually getting more complex. I already mentioned I came into this really after the sort of 8-bit microcontroller era, more in the microprocessor era. I went to university to get a computer science degree a couple of decades ago, we'll be vague. And the machine that I got my degree on, the machine I was doing my computer science program on, was actually much, much less powerful than the very cheap embedded devices that we see out there in the wild today. So, my computer was a single CPU, had very limited RAM and storage. A Raspberry Pi can have multiple CPUs. So these devices are massively more complex and powerful than anything that came before them. But at the same time, that complexity has another meaning. Because we have all of this power, we're asking these devices to do more and more with larger and more complex pieces of software running on them. Again, the microcontroller era, we were pushing things that were kilobytes, or maybe tens of K. Now we're talking about megabytes, hundreds of megabytes, even gigabytes of application code running on these devices out in the wild. And as you know, the larger your code is, the more complex your code is, the more errors there are going to be in it, and the larger surface for attack, surface for security vulnerabilities is going to exist. So we've got many more devices doing much, much more powerful things. You would think we'd have a lot more people working on this. But in fact, the opposite is true. If we look at the number of developers that are in the embedded world today versus the web and mobile developers, there's 600,000 embedded developers, 8 million web and 9 million mobile developers. So we have an order of magnitude more devices that are more powerful and complex than they ever have been before, and we have orders of magnitude fewer people building these things. So what do? We can really do one of two things. One of which is we can go on a crash program to educate a bunch of embedded developers and try to bring this up to 6 million or 10 million, whatever we need to do. But frankly, we don't have time to do that. We don't have the time and we don't have the resources to make that happen. So really the only solution is the other one of taking these web and mobile developers, taking the tools that have been built to allow these web developers to do multiple deployments to production per day, and bringing that tool chain to the embedded world. So making it possible for those 600,000 embedded developers to be way more productive, and make it possible, frankly, for the web and mobile developers to play in this embedded space. And this is what that tool chain really looks like. There's a whole bunch of tools that have been built up over the past couple of decades to enable this multiple deployments per day or per week model. And they make one developer really, really productive. So a single developer can work on code locally. They can do their local development, local testing, and then they can push that code up into a distributed repository and kick off a whole set of tools on the back end that are going to do automated testing, automated deployment, automated integration, sometimes even automated documentation, all sorts of automation that makes this developer orders of magnitude more productive than they would have been without it. And that can be deployed into production in a way that that developer is already familiar with. So if something breaks in production, the developer who wrote that code can immediately go into production and work on that code without having to learn a totally different environment. When they build that code locally, the same environment is running in production, even if different developers are running different environments. So what we really ought to do is take this model and bring it to the IoT world. So bring this to the embedded world. Take the same set of tools, push that onto embedded devices. And there's a bunch of these tools. Like I said, we've done this for decades. We have built up a huge array of tools to make this possible. All of these things are also open source, so they're things that we don't need to worry about reinventing or working out compatibility. All these things work together today. We can just pick them up and start using them. But I want to talk about one of these tools in particular, and that's Docker. And if people here haven't heard about Docker or aren't really familiar with it, Docker is a containerization engine. And what that means is it's a lot like a virtual machine. So in a virtual machine, you have an operating system, you have all of the libraries and support code, and then you have your application code all kind of packed into one single file or one logical group that runs on emulated hardware, so you're always getting the same environment every time. Docker is exactly the same thing, but without the emulated hardware. Docker runs natively on a device, so it basically runs inside of the Linux kernel that is hosting the machine. But everything else is the same. So you've got your operating system, all of its libraries and support files, everything you need to run your application plus your application code packaged up into one single file that can be then dropped onto an environment and run natively. And the cool thing about this is we can run different environments inside of Docker containers and all coexist on the same host. So if I'm building a web service, I might have one developer who really likes Red Hat. So they build the database backend in a Red Hat environment, package that up into a Docker container and deploy it. Whereas maybe I want to develop the front end and I've got a web server and I'm doing that in Ubuntu. I package all of that up and I deploy it. So I have my environment, the database developer has his environment, but they all run in these containers in the same environment. So we get a really portable way of working with the code that we need. Now, Docker was built for exactly those sort of purposes. It was built with the idea of doing this on vast server farms with arrays of identical hardware. The whole idea here is that if something starts to go wrong with my web server starts to crash, I don't really want to spend a lot of time trying to nurse it back to health. I'm just going to delete it or shut that Docker image down and bring up another one that is already healthy and already working. So the whole idea here is to do things at massive, massive scale with identical hardware. So you might think, Why in the world would I want to take something that was designed for massive server farms and put it on a single embedded device, right? If a Docker image in a server farm gets bad, I don't care, I just kill it. But if my IoT device that's running running a power generating wind turbine in the middle of the ocean starts to go bad, I really care about that. I don't want that thing to die. I can't just kill it. I want to bring it back to health. So why would I use that technology in the embedded world? Well, I'll give an example. A few months back, late May, early June, I believe, we were at the DockerCon in Seattle. So this is a Docker convention. And one of the things we did there is showed off some of the technologies using Docker on embedded devices. And I took this picture from the audience, so it's a little blurry, but the yellow dash kind of in the middle of the picture in front of the black screen in the background is a drone. So this is actually a drone flying on stage. And what we did was we updated the drone control software while the drone was in flight using Docker. And I'll explain how we did that. So we had a device on that drone, and it had a containerized application. So we had our application inside of a container. And you can see from that container, it's holding its shape, but there's something wrong with it. There's something not right with this container. We really ought to fix that. So what we were able to do is push a second Docker container onto that same hardware. So remember, because it's a Docker container, we can run multiple applications at the same time on the same physical hardware. So we pushed an updated version of our code in the new container, but we had both containers running simultaneously. So at this point, we really have two versions of our application running at the same time. And what that lets us do is hand over all of the state from the old version of the application, all of the control of sensors and gyroscopes and everything that's going on that device, we can pass that to the new container. And only once we're satisfied that the new container has control of everything, that everything looks good and we're ready, do we shut the old one down. So at no time is there really a risk of bricking this device. Even if the new container were bad, the old container can stay running, and the host computer, the host OS, is actually what's maintaining that internet connection. So even if I crashed both containers, I could still push an update to that device. It doesn't go offline. So using that model, we were able to update the drone in flight. And this is what the software on the device looks like. See, I promised we'd start to get into the technical bits. Now we're finally getting there. We have a Linux-based OS on the device, which we call Resin OS. It is open source. It is something that we have put together and made available to the community for running containers. And that is based on the Yocto project. And Yocto, for anyone who's not familiar with it, is sort of a toolkit for building very lightweight Linux images. So the whole idea here is we want something really, really thin and small, that all it has is the Linux kernel and really enough runtime to run the Docker engine. Everything else is happening in one of those Docker containers. So the application, just like I talked about on the drone, the application is running in a container, but even all of the update systems that we've built at Resin are also running inside of one of these containers. What that means is it's sort of like Inception. We've got containers all the way down. We can update the update mechanism using the update mechanism. So as we want to push new features or fix bugs in Resin, we can actually push an updated version of Resin, hand over control, and then shut the old version down. So the advantages of using Docker in this environment should hopefully start to become clear. I personally went from my reaction of why in the world would you put Docker on an embedded device to, after learning this, saying why in the world would you ever not run Docker on an embedded device? It just makes so much sense to use this model. But I want to show this off. I want to show how we can use all of these open source tools, this existing tool chain, to deploy updates onto IoT devices so that we don't end up spinning our wheels for the next 20 years trying to reinvent all of this stuff. So let's take a look. So I'm just going to switch to a different desktop here. I'm going to reload this so I know that it's working. And what I've got is, in the upper left here, I've got a webcam pointed at a fleet of Raspberry Pis. So these are just embedded devices, and they have screens attached to them, mostly so that you can see over a webcam that things are happening. These are actually running in our Seattle office at Resin, and I personally am sitting in Boston. So these devices are 3,000 miles away from me. I really, truly am managing them remotely. You can see the little Lego Space Needle next to it. That should hopefully prove that it's in Seattle. I can actually show off that we do some geolocation inside of our platform as well. So if I I zoom out here a little bit, maybe you'll believe me from the map that these are where those devices are sitting in Seattle. But over on the right, I've got a view of what Resin presents, the service that is doing this update presents out to a user. And this is these same devices being managed and monitored from inside of Resin. And again, Resin is really just combining that all of those open source tools and that open source tool chain that has been built up over the past 20, 25 years into something that works on IoT devices. So let's take a look at this. What I've got is an application that I wrote, and you'll see my application isn't exactly a really complex one. This is just to give you an idea of how it works. But this is an application that's running on those devices. And you can see I've got a bug on those devices. I've got a big, nasty red bug on those things. And I want to fix it. So this particular one is written in a shell script, which makes it nice and easy for me to edit. So I'm just going to open up the code of that application and fix my bug. This is usually where people laugh at me for running Nano instead of something like VI, but it has nice syntax highlighting and it's easy. So you can see, sample application. I'm just going to change the code here. So I'm going to change my bug to a fix. But this could be anything. This could be a C program. This can be Java. This can be Python. Anything that will run in a Linux environment can be used here. This is just the tool chain that enables device updates to happen. So I've made a fix, and I'm going to just go through the same sort of workflow that I would from a web application. So I'm going to check this into my source control system, which is Git in this case. So I say git add, git commit, fix the bug. So we'll put a nice commit message in there so that later on people know what I did. And now I'm pretty much done from my point of view. I would probably test this in the real world locally, but I'm pretty sure this is going to work. So I'm just going to push this out into production. And the way I do that is using Git's push functionality. So Git is a distributed version control system, meaning that I can push this up to a remote server or a remote Git instance somewhere and have that Git instance receive the code and do something. In this case, I'm going to push the master branch to the Resin servers. And what you'll see happen is Resin is going to receive that commit. We're going to start compiling that. In this case, there's no compile step because it's a shell script. We're going to build a Docker container. So we're building a Docker container that targets the deployment environment. And we're now pushing that Docker container into our container registry. When we see that unicorn, that means it's actually already done. The image has been pushed into the registry, and it should very shortly start to get picked up by the remote devices. They should see that there is a new update available and pick that up. Well, we're going to see if they do that. While I'm waiting for that to happen, I'm going to just drill into one of these devices and take a look at a couple of features here. So you can see, okay, we do actually have a download. Don't know why the status didn't update there. That's okay. We're actually receiving the image, and you can see we actually have console logs from each one of these devices. So because we can maintain a connection to these devices from the host operating system, we can actually see everything that's going on with a remote device just the same way as if it were sitting on your desk with a serial cable plugged into it. And if you look in the upper left, you can see that the fix has been applied, and these devices are starting to pick that fix up. So what we're doing is, again, we're pushing a new container to the device and bringing up only that container. So what you'll notice is the devices aren't rebooting. We don't have any downtime while we switch from the old version of the software that we had pushed on there to the new version. We just get the new version up and running. So again, for mission critical deployments, this is the sort of thing that we can do and deploy multiple times a day without ever taking a device down. So you can start to imagine this is a great way of dealing with security fixes, dealing with product updates, and dealing with a lot of functionality of devices out in the real world. So what I'm going to do is I'm going to pause for breath, take a breath, and see if we've got any questions. If not, I can always bore people with more slides, but let's take a look and see what we got. Let's scroll up a bit. Any software licensing challenges with Docker deployment? Great question. So I want to be very, very clear. Everything that I have been showing and everything that we do at Resin is open source. So Docker is part of that and is included. Docker is an open source technology, so you can pick this up and use that with no license fees, no concerns about using that with your code. It's also just incidentally not any sort of viral license, so there's nothing about your code has to be open source when you are running Docker or using Docker to deploy and manage those applications, or when you're using Resin. Your code can still be closed source if you want. It's just all of the tool chain that you are using to deploy is open source. Let's see what the next question was here. How would you propose we use microservices with Docker embedded deployments on microcontroller microprocessor? Great question. So I think there's a couple of answers that we can, a couple of ways we can approach that question. So one of those is microservices. Typically, if you're talking about microservices, you mean that you have a bunch of self-contained services or self-contained units of code that do not necessarily interact with one another other than through their APIs. So they're not one monolithic code base. You've just got them split out, and you want them to be able to talk to each other and do very simple actions for one another. You can do this exactly the way you would do it in a server environment on these embedded controllers. So anything that you can run in a Linux environment can run in a Docker container and can therefore run on embedded devices deployed through Resin. So you can either put all of your microservices into one Docker container and deploy those out onto your embedded devices, or you can deploy multiple containers onto a device. So if you want to have one container per service and deploy each one of those containers on a device, you can absolutely do that. I will caution you and say I would not recommend that deployment model for something that has a lot of different services, because there is a small amount of overhead for each Docker container. So if you do have to remember that you're deploying these things onto something that may have RAM measured in only a couple of 100 megabytes. So you're not going to have tons and tons of space to run a whole bunch of different instances with their own OS and their own environment. But you absolutely can do that as long as you take that into account. The other way that I would talk about that microcontroller microprocessor model is if you're talking about having let me make sure I get this right, microcontrollers working in concert with your microprocessor. So if you do have that sort of 8-bit microcontroller sensors that are in your environment, and maybe those are connected through something like Bluetooth, Bluetooth Low Energy, Zigbee, something along those lines, you still want to be able to update those devices, but they're probably not directly connected to the internet. In that sort of model, those microcontrollers tend to be connected to a microprocessor gateway. And we can support that model as well. So the way that works is there's just one extra step. You push an update to, let's just say it's a Raspberry Pi for the sake of simplicity. You push your update to the Raspberry Pi. The Raspberry Pi then runs a set of software that pushes the update to the microcontrollers. So it does the OTA flash to the microcontrollers that are connected to it. And then you would manage the firmware deployment for the Raspberry Pi through something like Resin. And Resin will report back status on, we call them dependent devices. So if you have a bunch of microcontrollers connected through Zigbee to your Raspberry Pi, you can do that update, and then you can see which of those sensors have been updated, which ones haven't, which ones were successful, etc. And all of the version numbers, anything that is supported by your controller that is reported back, you can report back through that model. Let's see, next question. How are you monitoring the performance? So let's take a look at this. So if I'm going to maximize this so that we can actually see a little bit more about the device. What we have in this model is devices that are always connected to the internet. So if I go back to my webcam and take a look really quickly, you can see the Ethernet cables coming out of these guys. They're just connected to our office network connection. So we know that we have a pretty decent connection to these devices. We can keep them online all the time. So we take advantage of that. We actually have a VPN service as part of the Resin platform, and each one of these devices connects up to Resin through the VPN and is passing data back in real time or very close to real time. So that's how we get things like console logs. If you want to pass back telemetry data, you can absolutely do that. There are people that are doing things like running top and passing a snapshot back through either the console log or through another logging service. You can pull down logs from devices. Anything that you want to pass out of those devices can be pushed up through that VPN connection. Now, if I've got a model where I don't have a constant connection to these devices, I've got something like maybe they're connected intermittently or through something like 2G or 3G where I really don't have the bandwidth to be just really, really chatty and passing all these messages back up. I don't have to have that VPN connection going. What I can do is I can tell the devices the frequency that I want them to check in, and they will check in through HTTPS at that frequency. So it really becomes a very simple model of them doing a poll, maybe once a day, once an hour, however often you configure, to say, hey, is there an update available? And maybe pass back whatever data you have defined that is most important to you. So you don't have to have that model where you have all of the data being passed up. But I do want to say it is really cool if you do have a constant connection to a device. So Ethernet, Wi-Fi, 3G, 4G, something with enough bandwidth to do it, because you can get not only this console view, but we actually pass back things like a remote shell. So I can actually connect to one of these devices that is sitting in our office in Seattle, and I can interact with that device. So if I want to do remote debugging or remote work on a device, I'm sitting in the application container on that device inside of the Seattle office, and you can see that's the same code that I had deployed or had in my local environment deployed on here. Should be even including the update because I pushed the update. Yep, there's my fix. So there's a lot you can do with this model if you have a constantly connected device. Let's see. That's really cool. Yeah, thank you, Maxim. I appreciate that. I thought it was really cool too. I get really excited about this, so I'm glad to hear when other people get excited as well. And Jason says, what's your vision on interoperability and compatibility for IoT? I'll talk a little bit about that, but Jason, I may ask you to elaborate on what it is that what you mean, or give me some specifics there. What I'll say from a very general viewpoint is that we at Resin, like I said, kind of view ourselves as plumbing. We don't, let's switch back to the webcam. Maybe you guys can watch me talk. We don't see this as another platform to lock people into, or something that is, hey, we're gonna get everybody on our platform, and this is going to be the only place that people work with IoT devices. Frankly, I think that model is ridiculous and broken. We saw that the web was successful by being an open platform and being very interoperable with everything around it. We want to do the same thing. We want to play really nicely, and that's part of why we do everything in the open. We're an open source company. We use open source tools to build all of this. We don't want to be some sort of lockdown proprietary model. We do want to be interoperable. So one of the ways we are pursuing interoperability here is, again, with the open source model, we make it really, really easy to add new hardware to the platform. So if you have a device, you have a custom device that you've built, we have instructions on how to build Resin to put it on your device. So you don't even need to work with us to get this running on your device. We also are using standard tools wherever they exist. So Docker is kind of the de facto containerization standard. There are other ways to do containers in Linux. Docker is really where the momentum is, so that's what we work with. We use OpenSSH, OpenVPN. We use HTTP, HTTPS for everything. We have an open API. So if you want to tie our API and manage your devices without ever seeing the Resin platform or the Resin interface, more power to you. We welcome that. So any way that we can be interoperable and work with the wider community is what we want to do. So I hope that answered your question. If not, feel free to just throw another one in there. And Jubel says, thanks for sharing these. Yeah, you're absolutely welcome. You're very, very welcome. Like I said, I get excited about this, so I love to share it and get other people going. Please feel free to submit more questions. I think I've gotten through all the ones that are there, so I've got just a couple of more slides. I actually don't really like slides. You wouldn't guess it from the fact that I'm showing a ton, but I'm going to just show a couple of more really quickly, and then if there are more questions, we'll hit those. Go back to screen sharing. So I just wanted to talk really, really quickly about more open source stuff. Like I said, we want to be interoperable. We want to be open. So we're doing a lot of really cool things. I want to brag about that. I don't think the team at Resin brags about it enough. So one of the things we did, one of the problems we encountered as we were building Resin, as we were putting it on the 20 some odd devices that we support today, is that it's really painful to do SD card flashing or USB stick flashing from a bootable image. And that's really anywhere you go. It's painful on Linux and OS 10. Anybody who has spent a lot of time with DD knows there's a reason that people call it disk destroyer. I've personally blown up a couple of laptops myself with DD. And the Windows tools really aren't that awesome either. They're a little clunky. And plus, having different tools on different platforms meant when you were writing out instructions, you had to maintain instructions for Linux and Windows and Mac OS. And it's just a pain in the butt. So we wrote a tool called Etcher to do this very easily, very safely, and cross-platform. So you can go to etcher.io, download this tool, use it to write SD cards or USB sticks, and then you really only need to write one set of instructions, and you don't have to worry about blowing up your hard drive. It won't let you do that by default. You can overwrite it. There's a checkbox that basically says, I know what I'm doing, but by default, you can't overwrite your own hard drive. So it's a really cool tool. Does one thing, but it does it really well. And like I mentioned earlier, we have put out Resin OS as another open source project. So even if you don't want to use this whole update and remote management model for embedded devices, you still might want to put containers onto an embedded device. You know, it's great to have a starting point to be able to do that, something that really is stripped down and lightweight and only has the bits that you need to be able to run containers on an embedded device. So, you know, we had to build that as part of building the Resin platform. We sort of looked around and realized this can be really useful even outside of Resin. So we split it off. It's a separate open source project. You can go download it and start putting containers on embedded devices. We'd love to hear from you if you do it. I'd love to hear your feedback. And you know, being open source, of course, pull requests are welcome, but go out and grab it and have fun. And all of this stuff, by the way, is up on GitHub. So if you look for us on GitHub, we are resin-io there because you can't put a dot in your name on GitHub. This is also linked from resin.io. So if you go to our website, there are links to all of the GitHub repositories. So you can go grab this stuff and start playing with it. We'd love to see what people can build on top of this. So that's pretty much it for me. Like I said, I'll come back and check and see if there are any more questions. But anybody has any questions outside of this, or you want to get in touch with me and talk about Resin or just IoT in general, hopefully you can tell by my voice, I get really excited about this stuff. I get really enthusiastic about what we can build. And yeah, there are problems. There are things that are wrong today, but we can fix those. I want to make the Internet of Things the next internet. I want to make this a cool platform that everybody can do really amazing things on. So please reach out to me and help me do that. I'd love to hear from you. Let's take off the screen sharing and we'll check and see if there's any more questions here. So Sunny Singh says, microcontrollers that only run firmware such as Firmata, how does Resin.io build the deployment fault tolerance, e.g. rollback changes? Great question. So I want to emphasize that Resin really targets Linux devices that can run Docker. So we are not really, the Resin platform is frankly too heavyweight to run on a device that size. So a microcontroller device is not going to run Docker. You're not going to be able to do that. What we do is we provide you the platform where you can push your over-the-air update to those devices. So you can push your firmware through that, through a gateway device, through your Raspberry Pi, push that out onto the updatable devices. But the Raspberry Pi itself needs to be aware of, or whatever you're using, your gateway needs to be aware of how to do the rollback on the microcontroller. Unfortunately, there's no industry standard for microcontroller updates. Everyone has their own way of doing it, and there are hundreds and thousands of those things. If we tried to write a generic way of doing that for the entire IoT with microcontrollers, we'd still be doing that 10 years from now. So it's the story is frankly not as great on microcontrollers, and that's just due to a limitation of the platform, of the microcontroller world. I mean, having said that, there's a lot of talk about Moore's Law being dead. I don't think that's true. I think even if we start to see fewer and fewer updates in the number of transistors we can pack into a square inch, that doesn't mean that the silicon that we have isn't going to keep getting cheaper. Look at the price of microprocessors and how that has come down year over year. If we stop building new fabs because we reach the end of life for silicon or the end of improvement for silicon, that just means that microprocessors are going to get orders of magnitude cheaper because we no longer have to recoup the cost of building fabs. So a Raspberry Pi or equivalent device that costs $20 or $30 today might cost $2 or $3 in the future, meaning you're going to see that level of power in smaller and smaller applications. So you'll be able to continue to use this model and update those devices. You're going to be able to update more and more devices using this model. So I think it's a bit of forward-looking for Resin and for where we see the industry going. And Sunny Singh also says, also we recently won IoT BC IBM Hackathon in New York City, and you'll reach out to me. Awesome. Congratulations. I'm glad to hear that. BC being blockchain for people who didn't know. So are there any other questions? I know we're bumping right up on the end of time here, and I'm sure people want to head to other sessions as well. So I can sit here and talk about this all day. Like I said, if people have questions or you want to talk to me, I'm Ronald McCollam, at Ronald McCollam on Twitter, ronald@resin.io. Please reach out to me. I'd love to talk to you. Thank you all very, very much. Cheers.